Now we're going to take a look at connectors. I'll throw some pictures up here because it's really hard to draw them. I don't know why I'm showing this connector. I just am. It's kind of obsolete. I haven't seen this in an actual installation ever. I've teach people how to make them. But here you go. This is the ST connector, which is a bayonet type connector. It's modeled after the B and C connector where you push on, turn, and connect it. But what's the most popular connector I've seen, and from what I can research, is the most popular connector is the subscriber connector, or the SC connector. And this is just a square connector, and it's just a push in, pull out type of connector. And another one that's I don't see very often, but apparently is common, is the LC, or lucent connector, which is much smaller and has a much smaller ferrule. So if we look at the connector, so here's the main body of the connector. And there's a little thing that sticks out, and the fiber is right down the middle of that. And that's called the ferrule that connects to that protects the fiber. And so that's usually made of zirconium ceramic material of some sort. It's white, very fine ceramic material. And the fiber is right down the middle. And so when you're putting these connectors on, you want to make sure you only have the glass, get all those buffers off, because that's just big enough to get the glass in there. And on the LC connector, it's much smaller than on the other connectors. And another connector we have is the MTRJ. That stands for multiple termination, I believe. RJ comes from its resemblance to the RJ45 connector. This is typically used for duplex connections, so there's actually two fibers in here. Plug it in, and so you get both transmit and receive, unlike the SC connector, where sometimes you'll find those connected together, two SC connectors with a clip, and you use them both at the same time, or they have to be used one at a time. The MTRJ, two fibers, transmit and receive, one connector, click it in. Actually never seen this in the wild, but apparently it's popular, so I added it to here. And then another one, the MPO, which is a multi-fiber push-on, also called the MTP, which is a trademarked name for the same thing, and it's used for ribbon cables. So one connector and a whole bunch of fibers in a ribbon for the MPO or MTP connector. And another thing about the connector is color. If the connector is blue, it's single mode fiber. If it's beige, it's multi-mode fiber. And if it's green, it's APC, or angled physical contact. So what we want to do is get two connectors together. So whenever we're connecting two fibers, whether it's two connectors, or this might be the receptacle in a switch or something, we want to get the two ferrules to connect straight to each other. And there's a little bit of a curve to it. It's getting a little scientific here, but the ferrules have a slight curve. And the idea is that curve is just enough that, yes, there is a little bit of give. You push them together, it pushes those fibers together, and they go into what's called optical contact. This is something that happens if a surface is very highly polished. They almost become one piece of material, and so there's very, very little reflection between the two. I had a story, a friend of mine who used to be an optical technician was working with some optical flats, and the way you test it is you have a test flat, so it's just a little disc of glass that's perfectly flat, no coating, and you take the flat you're making and you put it on top of there, and when they come together, there's going to be light coming in, there's an interference pattern, and if the lines are straight, then you know that they match. But if you see curves, you know they don't match. But what he saw, he put it down, he saw those interference patterns go zoop, and he heard a click. They went into optical contact, and he could not get them apart. They were basically now one piece of glass. Since they were different types of glass, he was able to put them in an oven and heat them, and because of the differential expansion, he was able to get them apart. But he almost ended up with a piece of scrap because of this optical contact. Well, that's basically what they're trying to do with fiber optics, is get those two fibers in optical contact, and so they have just the right curve of that ferrule to get those two pieces of glass to come together, and the force flattens them out, and they go into optical contact if you have a really good polish on them. And so that's the idea, is to get that optical contact, and that's called ultra physical contact, or UPC. But there's still a problem. We can't get rid of the reflections that we're going to have at this interface entirely, but we do a pretty good job with the UPC. But there's another one called APC, where these ferrules are polished. I'm going to exaggerate this, of course, here. More angled, and that angle is 8 degrees, so that's APC. And what that does is when they come into contact, any light hitting here, if it goes through, it goes through, but if it reflects at an angle high enough that it's greater than the critical angle, and out it goes and doesn't reflect back through the fiber. So that's what an APC connector is, and that is green. Okay, now I don't know if as an electronics technician you're ever going to put connectors on cables or splice them, but we'll talk a little bit about that. You know, in my fiber optics class I taught people how to put fibers into connectors and how to test them, because employers expected them to know how to do it, but then they get on the job, they never do that, because you buy pre-terminated pigtails, as they're called. So you have a fiber already on the connector, so you either have a patch cable or a pigtail has a connector on one end, the other end is open that you can splice onto another cable. But anyway, we're not going to talk about making the connectors, that's for the fiber optics class. But we'll talk about splicing real quickly. There's two types of splices. There's a butt splice, where basically the fiber optics are put into a tube and butted together. And then we crimp them in there, and that is a butt splice. But a better splice is a fusion splice, where we take the two fibers, we cleave them off, so we don't have to go through any polishing step. As a matter of fact, even with the butt splice, we don't really polish them, we cleave them. What we do is we have the fiber, we want to make a surface to go into the splice, so we scratch it with a device that puts a little bit of a scratch in it, and then we give it a little bend and it just snaps right off like cutting glass. And if it's done right, we get a perfectly flat surface that doesn't need to be polished, and we put those together. And same thing with a fusion splice, but instead of butting them together and crimping them, we put it into a device that has a couple of electrodes, if I can draw them here, and we get them to just the right distance, not quite touching, there's a just right distance. And this is all done by machine now. In my class I had a fusion splicer where we did it by hand because I wanted them to learn the nuances of it. But then we showed them how a modern fusion splicer, where it's all done by the machine. You cleave it, stick it in, and press a button. But anyway, it moves them to just the right distance, aligns them, and then with them just the right distance, it puts a high voltage across these two electrodes. And if you have a microscope where you can watch it, you can see the little zap. That's why I like the little hand splicer I had. It had a microscope where you could actually watch the fusion happening. Modern ones use cameras. The camera's overwhelmed by the brightness, so you don't get to see anything. But anyway, that spark melts the glass and it fuses together, and you have a slight little dip, but it's calculated to be just right. That's obviously exaggerated. And you end up now with one piece of glass, and so there's no possibility of reflection. So that's what a fusion splice is. So most likely, if you work with fiber optics, you're going to do fusion splicing, but the splicers are started around $10,000 or something like that, so it's pretty expensive. So if you need to do a few splices, you might want to use butt splices. You can buy them for a couple of bucks each. But if you're going to do a lot of splices, of course, you're going to use a fusion splicer. Blends together, flashes a little spark across these to clean it up. You push the button, whether it's a single splice or a mass fusion splice, it'll zap that to clean up any garbage, and then it'll fuse them together. And so a mass fusion splicer will fuse ribbon cables together. So that's how cables are spliced. Cleaning, basically you use lint-free pads and isopropyl alcohol or some other cleaner that's made for fiber optics. There are also other fiber optic cleaning things. Some of them are little sticky things where you uncover some pads. You just go, hope that little sticky thing will take any debris off of the fiber. There are little fiber optic cleaning things. It's like a cassette with a tape on it, and you pull a trigger, it exposes the tape, you clean the fiber, let go of the trigger, and it advances the tape and covers it up. What you don't do is you don't, no, we don't clean fibers that way. Yeah, we don't want any debris of any kind on these fibers because we've got a very, very tiny light channel. That core is very tiny, and a little piece of dirt, debris, dust, smoke, or whatever is going to block that if we get it in there. So we have to be very clean when we work with these. One of the things we teach is that you don't use fusion splicers in manholes. So if you're down in a manhole doing some splicing, which you're probably not going to be doing as an electronics technician, but you might find yourself down there with the guy working with one, and no, you don't use them in manholes because gases can get in there from nearby sewer lines that can be explosive. And sort of reminds me of the guy who was skydiving, and he jumps out of the plane, he pulls his ripcord. These days I guess they toss their little pilot chute, and the parachute didn't come out. And couldn't get out, so he just no problem. Rolls over, pulls the handle on his reserve chute, nothing happens. So he's falling down there trying to contemplate what to do next, and he looks down and he sees a man coming up from the ground at him. He's falling down, this other man is coming up. And so as he passes, he says, "I'm skydiving, what's happening to you?" And he says, "I'm lighting a Coleman stove." Where are we going now? Testing. Okay, different ways to test fiber optics. Let's say you have a dead fiber. You suspect it might be broken. You can use what's called a visual fault locator. And this is basically a laser pointer, except it has a lens that focuses the light right on the core of the fiber. So there's your ferrule, your fiber's right in there, and we have basically a laser with a lens that focuses right on there. I tried this with a laser pointer, it doesn't work. You have to get that light focused in there properly. And you get that visual laser, usually red laser. I've never seen a green one, but could be. You get that red laser going through there, and if there's any break in the fiber, you look along the fiber and there's a bunch of light leaking out right here. That's where your break is. And you can also, just to show that it happens, you can wrap that fiber around your finger and it'll light up because you're getting too small of a turn and the light now no longer goes through at the critical angle and starts to escape from the fiber. So in fact, there are ways to get information out of a fiber that hooks onto it and bends it so that the light comes out in a little photodiode that can read the light in the fiber without being at either end or without breaking it. So that's a visual fault locator, just basically a little laser. As an electronics technician, you're probably not going to be testing fibers, but you might. So there's a kit called an optical loss test kit, and basically put the diagram of it up here. So we have a light source over here somewhere. We have what's called the launch cable, which is just a patch cable that goes to a two-way connector called a barrel connector, and that connects it to the fiber that's being tested somewhere around here. So those little circles are the fiber you're testing. Goes to another barrel connector to another patch cable to a power meter. So we have the launch cable, the fiber being tested, and the receive cable. And the power connector measures power in dBm. And if you go back to our talk about decibels, remember that decibels is always a ratio unless you put a letter after it. dBm means that we are comparing our power to 1 milliwatt. So if we have a power meter, an optical power meter with our fiber coming in it, and it says 0.0 dBm. What's that telling us? Well, it's telling us that power coming in is the same as 1 milliwatt. There's no difference between 1 milliwatt and that power. So 0 dBm equals 1 milliwatt. Now what happens if I see minus 3 dBm? Well, 3 dB is a ratio of 2 to 1, so if we're cutting that in half, I have 0.5 milliwatts. So see how that works? So positive 3 dBm is what? 2 milliwatts. So 3 dB is a doubling or a halving. 0 dBm equals 1 milliwatt. Anything less is less than a milliwatt. Anything more is more than a milliwatt. And so what you're going to do when you're testing a cable is first you're going to put that launch and receive cable together and get a baseline reading. And so your power meter says minus 20 dBm. I don't think that's an unreasonable number for the amount of power from the light source. And so now you've got the launch and receive cable together. You've got your baseline measurement. You pull those apart, put in your cable being tested, and now the meter says minus 23 dBm. What's that telling you? How much loss do you have in dB? Well, if you start with minus 20 with the cable not in there, and you put your test cable in there, now you're losing 3 dB, go from minus 20 to minus 23. What is your loss? Ain't that easy? No calculations from watts to dB. You just take the difference between your two dBm measurements, and that's your loss in decibels. A typical link loss budget, which means the amount of loss they can allow in a whole set of splices and connectors and whatever between 2 points, is typically around 20 dB. So we can have down to minus 40 dB on a long cable with lots of splices and connectors and still be within our budget, which is calculated when you make the installation. So another thing that you might hear about or see, who knows, is the OTDR, the Optical Time Domain Reflectometer. Ooh, fancy word for this device. It's basically radar that sends down, maybe LiDAR if you want to be correct, sends a pulse of light, laser light presumably, down the fiber. So here's our OTDR. We connect a fiber to it and it goes wherever it goes. And we have a display on it. And I used to like to use one that was an old analog one with the CRT display, because once again you get a feel for what it's telling you. And then we would give them a more modern one which gives a digital display. But anyway, what it's going to do is send a pulse of light. So the light here turns on, the light turns off, and there's that pulse of light, and it's going to start traveling down the fiber. Now as it travels down the fiber, some of that light is going to be scattered back. And so that light comes back in. And so we turn the light on, turn the light off, and then we watch for what comes back. And so while that light is on, we can't see anything. So let's go ahead and kind of draw what I'm going to put up here. Just draw it by hand here. Here's our distance scale. It's basically a time scale, but we know how fast the light is traveling through the fiber. We have to set up the OTDR for the particular index of refraction of the fiber we have, if we can find it. That might be in the invoice, might be in specifications at the manufacturer. It's a little hard to find, but it's typically going to be about 1.5. And then here is our reflected power. They label it as attenuation, but it's really reflected power. But since they label it attenuation, I'll do the same thing. But basically it's telling you how much power is coming back. So when it turns on that laser, we get a lot of reflection back, so a lot of power coming back, but then we turn it off and we start watching for what comes as that pulse of light travels down the cable. So this is all happening very quickly. That light is traveling at perhaps 2/3 the speed of light in a vacuum. So it's going down very quickly, but we have this high-speed equipment that we can see what's going on. So the initial pulse, can't see what's going on because we're getting all that reflection back. We turn that off and now we just see what's coming back as that pulse goes down the fiber. And so as it goes down, we see so much power coming back, but that power is attenuated as it goes down, so it gets less and less and less. So we see that our reflected power goes down with time, which equals distance, because we know that how fast that light is traveling. So let's say we hit a fusion splice. That splice is not going to have any back reflection, but we are going to lose power there. And so we're going to see a little dip. So if you see a dip, what's that? That's a splice. But now we get to a point where we get a reflection. So all we're getting is backscatter, 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 but now we hit a interface between two fibers at a connector, and we're going to get some back reflection. So we get a spike, and then when it finishes reflecting, oh, it's gone down even more. So that's a connector. And then we finally reach the end of the cable. Well, that end of the cable is going to be a glass to air interface, so we're going to get a Fresnel reflection. And so we get another reflection, and then nothing, and then we just see the noise in the system. So that's the end of the cable. So that's a good cable, good even losses there, not too much loss at the connector, fairly desirable. If we see the cable goes, let's see, there's our initial pulse, and it goes so far, and we get a spike and then noise. That looks like a break in the cable to me. If we're going down, and we get a spike and a lot of loss, that's possibly a break in the cable where some light is getting through, but more likely as a cruddy connector, maybe a connector that needs to be cleaned or redone or something like that. So that's just a little bit about what the OTDR can tell us. It can tell us how much loss we have, but it's not as good as a source and meter to test. So if you're testing for actual optical loss, you need to do the source and meter. The OTDR is really for fault finding to make sure that everything looks good. So you get your installation, you stick the OTDR on each cable, see a good connection on each one, not too much loss at our splices and connectors, we have a good to go installation. So that's the OTDR. So finally, safety. You're going to be, if you are a fiber optics technician, which I'm presuming you're not because this is for electronics, but you still might do some cleaning, you might work with some hazardous chemicals like isopropyl alcohol. Well, take proper safety precautions with whatever chemicals you might be using. You might be using other cleaners. Be sure you understand the safety aspects of it. But another thing to remember is that what are we shining down this fiber optic? Often it's not lasers. What color are those lasers? Infrared. You probably can't see them. If it's 850 nanometers, yeah, you can see that. But 1,000 nanometers, forget it. So I don't see anything in this cable. I don't see anything anywhere now. So you want to be careful about that. Remember that you're working with lasers. Don't be using a microscope. That's another thing I probably won't be using, but technicians will. They can stick a connector in a microscope and say, oh yeah, that's a good clean, that's a filthy dirty connector or whatever it is. Or somebody didn't even polish off the glue or whatever. Don't be putting connectors up to your eye through the microscope unless you are absolutely certain that there's no laser light coming through it. So you have to make sure it's shut down, make sure there's no light going in there, and if you pull it out, tag it, make sure the tag says do not plug this in, because that is a safety issue. Now that being said, the lasers used to feed fiber optics are of a low enough power that according to ANSI standards they are not hazardous, but why take a chance? Don't be sticking that up to your eye. So anyway, that's what I think you need to know as an electronics technician about fiber optics. So I hope you found this useful and informative. If you did, please give me the thumbs up down below. That really helps the channel. Don't forget to subscribe and hit that gray bell when you do, so you get notified when I put up new videos. And if you want to learn electronics technology, you can go to Vocademy.net and take my free electronics course. And as of now, I am still avoiding putting commercials on these videos because I'm depending on you to make all this possible. So to help me make these videos, and to keep Vocademy free, you can support me by going to patreon.com/Vocademy and pledging your support. Or if you want to make a one-time donation, which I really love it when those come in, you can go to paypal.me/Voced, V-O-C-E-D, and send me a one-time donation. So a big thank you to my patrons and my one-time donors. I could not do this without your support, and thanks to everyone for watching.